before we do physics? I think the answer is no. Yeah, so let's get to it. So last week we spent the entirety of our class time talking about mathematical definitions and how to do really basic statistical kinds of calculations. And so I promised you today we're going to actually start doing physics, all right? And so that's what we're going to do. So let me pull up my iPad. Gotta hit the share button. There we go. It seems unnecessarily convoluted, but what can you do? All right, there it is. Look, I've even already written the date. I'm so ahead of things. All right, so as I promised, what we're going to start talking about today is what's referred to as a random walk. Okay, and random walks are, as a physicist, I would say insanely important. So a lot of my research has to do with statistical mechanics. I think that's probably why they asked me to teach this class. And anytime I encounter any kind of theoretical problem, I ask myself two questions. One is, how do I make this problem look like a random walk? Okay. And if the answer to that is I can't, then the second question I ask myself is, how do I make this look like an Ising model? And we'll talk about that towards the end of the quarter. All right, so in other words, as a statistical mechanician, I guess is the word, two of the most important models we're going to talk about are random walks and the Ising model. And so today we're going to start talking about random walks. So as a physics type person, if you don't already know these things, then you should learn random walks inside and out because they show up everywhere. All right, so now, in particular, what we are going to talk about random walks is we're going to talk about them within the context of Brownian motion. Okay, and so Brownian motion is where you take some little tiny particle and you suspend it in some kind of solute. So whether that's a gas or a liquid like water or what have you, it's just a tiny particle that's suspended in some solute. And so now what happens is, let's say that our tiny particle, let's do black. So these are our particles. Okay, there's a bunch of particles. And if you suspend them into a solvent, then we also have to draw the molecules of that solvent. So let's imagine that we got little molecules of air or little molecules of water or whatever. All right. So the blue here is our solvent. That is something like water or air, where air is primarily nitrogen, something like that. And then these black particles are our solute. So that can be whatever you want to think about, all right? So now what's going to happen is if you do this and then you look at what happens to your solute particles on a microscopic scale, so like you take a sample of this and you put it under the microscope, what you're going to see is that everything is not stationary like you see I have it drawn here. What you're going to see is if the solute molecules are large enough, instead of just sitting there stationary, what's going to happen is you'll see them jiggle around, okay? So all these particles are not going to just sit there in a stationary fashion. They are going to jiggle, all right? So we're on the internet. Why not take advantage of the internet? So let's take advantage of the internet. So now we're going to go to YouTube. And I'm going to show you an example of Brownian motion. Share. Why do I have to hit the share button? I already told the damn thing I want to share. Why do I have to hit it again? Anyway, all right, so here is a random YouTube video that I found on YouTube where this guy took some grains of pollen from a tree or some other, plant and suspended it in water. And then you stick it under the microscope and here's what you see. accompanied, of course, by tinkling piano music. So there's, I think, these big blobs or whatever are in the plant that are secreting the pollen, and then you can see these little circles, okay? So there's the pollen grains. They're suspended in water, so you can't see the individual water molecules, but you can see the pollen grains. And you can see that they're not just sitting still, they're jiggling around. All right, oh man, it's so relaxing. Thank you. I didn't catch the name. But in any case, okay, so that is Brownian motion. All right, now I got to get back to my iPad. Here we go. Oh, I think my YouTube is still running. Comical. All right. No, stop YouTube. This is some professional lecturing going on here. All right, so we're back at the iPad. Everybody can see the iPad again, yes? All right, very good. Okay, so what you just saw in that video was what I tried to draw with my limited artistic abilities. That is, you have some large particle that you suspend in a solvent, and it jiggles around. So now, why is it jiggling around? So that jiggling motion is what's referred to as Brownian motion. And now the question is, why is it doing that? And I'm sure you all know the answer. That's what's happening is that our solvent molecules are not stationary. They are also flying around, okay? So all the solvent molecules are also flying around, like so. And as we will show in a few weeks in subsequent lectures, the speed with which these solvent molecules are flying around depends upon the temperature of the water. So the hotter you get it, the faster they go. Okay, and so now what happens, what you're seeing is the jiggling motion is that the water molecules are colliding with the pollen grains and rebounding. So it's a collision, just like you learn in physics 1A. Okay, and so what happens is during that collision, you conserve momentum, and that causes the pollen grain to also get displaced. It also undergoes a collision, right? And so it moves. And then it collides with another one, kapow. And so it moves again. And so what happens is that the solvent molecules are continuously bombarding these particles, and as a consequence, they get knocked around in some more or less random path. All right, so now what we're going to do is we are going to model this Brownian motion, and we are going to model it as a random walk, what's mathematically referred to as a random walk. And what I'm going to show you is that, so what we're talking about here is how each one of these particles moves from a microscopic viewpoint. And what I'm going to show, so this is the microscopic picture of what's happening. And what I'm going to show you is that using statistics, specifically statistical mechanics, that if we look at the probability distribution of how we expect a large collection of these random walkers to behave, what we're going to get is what's referred to as an emergent phenomenon. That is, it's some complex, higher ordered behavior that you wouldn't necessarily expect to happen just by thinking about the behavior of an individual particle. But when you get large collection of these particles together and they start interacting with one another, you get some more complex pattern emerging from that large scale behavior. All right, so this emergent phenomenon we're going to show exists is what's referred to as diffusion. Okay, and this is, again, this is going to be on the macroscopic scale. So this is if you like have a glass of water and you squirt something in that glass of water, you can see those particles start to spread out. That is diffusion. All right, so let's do it. All right, but now before we start talking about Brownian motion, I want to talk about I would say a more abstract model. So before we start specifically talking about things Browningly diffusing, let's go back to our old friend, the coin. All right, so what we're going to do is introduce the idea of the random walk and how we're going to treat it through what we've been talking about previously, that is random coin flips. All right, so let's go back and let's consider flipping a coin. Flipping a coin. All right, so now if I flip it, it's what we referred to as a Bernoulli trial, right? So it has two possible outcomes, heads or tails. All right, and what I'm going to do is define a variable called S sub n. Okay, so now n here refers to the number of coin flips we're talking about. All right, so if I just flip the coin once, then n is equal to 1. If I flip the coin twice, n is equal to 2, so on and so forth. Okay, so n is the number of coin flips that we're talking about. S stands for sum. All right, and so what S is going to tell me is I'm going to flip the coin n times. I'm going to keep track of how many times it comes up heads and how many times it comes up tails. And what S sub n is just the number of heads that you get minus the number of tails that you get. Okay, so in other words, it's telling you the excess number of heads that you have after n attempts at flipping this coin. Okay, so now we flip our coin. Here's my coin again. We flip it, and our outcome space is heads and tails. Okay, so now again, we need to assign a random variable to heads or tails so that we can do math on it. And so the random variable that I'm going to use I'm going to call it L. Okay, for reasons which sound kind of stupid right now. I mean, why are you going to call it L? When we start actually talking about random walks, it'll become clear why I call it L. All right, so L is the random variable that takes these two outcomes and then maps them to a number. And specifically, the numbers that I'm going to use, or I'm going to call heads, is +1 and tails is -1. Okay? All right, so S sub n, written in terms of that variable, is all I'm going to do is I'm going to flip a coin. So that's going to be L1, right? If it comes up heads, I add 1. If it comes up tails, I subtract 1. And then I flip it again. And I'm either going to get plus or minus 1. And what S sub n is, I'm just going to take each of these outcomes and then add them together. Like so. All right, does that make sense? All right, very good. So in other words, what I'm doing here, so let me draw this graphically. All right, so here on my coordinate axes, my vertical axis here is going to be n. All right, so that's the number of coin flips I have. The x-axis is S sub n. Okay, so what happens is, let me switch to a different color so we can see it. So I start off here at the origin, and then I flip a coin. So I flip, I come up here to n equals 1. And then at n equals 1, I'm either going to get heads, which means I go to the right, that is +1, or I get tails, and I go to the left, -1. So let's say I flip it and I get heads. So I would come over here. Okay? So this would be L1 equals +1. And then I flip it again, so I come up here to n equals 2. Okay, I flip it again. If I get heads, I go this way. If I get tails, I go the other way. All right, and so you can see that what's happening is that this is kind of like a playground that I'm walking around on. And as I make more coin flips, I'm heading this direction. And the direction that I'm moving along the x-axis is random. Okay, does that make sense? All right, very good. Okay, so now the next thing we're going to assume is that our coin is fair. All right, so that is the probability of getting heads and tails are equal. So specifically, the probability, oops, let me get back to black. Ah, AC/DC, fantastic. Back to black. back in, well, you know what I'm saying. So probability of heads. So in terms of our random variable L, that's what I would call the probability of getting +1 is 50%, or 1/2. Similarly, the probability of tails, that is the probability of getting -1, is also 1/2. Okay, so they are equal and both equal to 1/2. All right, so now that is our random process that we're going to be talking about. And so now what we want to do is start asking about the statistics of this process. So for example, so again, what I have here, this is a random walk, right? So I have my playground and I am randomly walking back and forth on that playground. And so you can start asking questions like, you know, if I do this many, many times, how far on average am I going to travel, right? So how far, so if I start out here, again, let me go to a different color. If I start out here and then I go in flips, so I travel some distance along my y-axis, come up here, I'm going to find that my walker has traveled some distance. And I want to know, on average, how far is that going to be? So things like that, okay? So the way that we would write that mathematically, if we're interested in calculating, so what we're doing here, this Sn is the distance it's walked, right? So if Sn comes out to be positive, that means we've walked this way. Okay, and the larger Sn is, the further we've walked. If Sn comes out to be negative, that means we walked this way. And again, the larger the magnitude, the further we've gone. Okay, so if we're interested in how far on average do we travel, then what we want to calculate is this, the average or the expectation value of S sub n for whatever n is. Okay? All right, so now, what is S sub n? So you can just use, we don't even have to do any math, right? All we have to do is, you know, rub our temples and use the power of our minds, you know, to see that, you know, the probability of going right is equal to the probability of going left. So anytime I observe a random walker that happens to go, say, over here, I have an equal probability of observing another one that goes over here. All right, so no matter where my random walker goes, because of the symmetry of the problem, I'm equally likely to find another one that's gone the same distance on to the other side. And because this side is positive and this side is negative, then on average, we're not going anywhere. Okay, does that make sense? Okay, good. My favorite number, 0. Zero's just the best. I love 0. I love you, 0. Okay, so that's boring though, all right? It's boring. On average, no matter how many steps you take, you don't go anywhere. And the reason this comes out to be 0 is because of symmetry. Okay, so this is 0 because of the symmetry of the problem. All right, and the symmetry is that this direction and this direction are exactly equivalent, except this one is positive and this one's negative, and when you add them together, you get 0. All right, so in other words, if we want to get something interesting, what we have to do is break the symmetry. Okay, and again, the symmetry here is plus and minus. I add +1 to -1, I get 0. That's symmetry. So now what I'm going to do is I'm just going to take, I got +1. Oh, I'm going to make the -1's plus as well. So I just make everything positive. How do I make everything positive? I square it. Okay, so instead of looking at the average of S sub n, what I'm going to do is look at the average of S sub n squared. Okay, and because when you take a variable and you square it, that maps all of the negative values onto the positive side of the coordinate system, then everything, so you've broken the symmetry. Now, instead of looking like this, now everything is over here. And what you can do is calculate on average, how far do I move away from the axis? Okay, does that make sense? Wunderbar. All right, so what we're going to calculate is the average of the square of S sub n And again, if this is like a distance, so if S, oops, so S sub n is like a distance, so that means S sub n squared is like a distance squared. That doesn't really tell us, that's a weird thing to think about, right? So in order to describe this in terms of, you know, a more intuitive distance, what we're going to do is take the square root of this. Okay, so what we're doing is taking the root, square root of these little pointy brackets mean we're taking the mean, and of the square. So this is what's referred to as the root mean squared distance. Okay, so whenever you calculate the root mean square of something, the reason you're doing that is because you have this symmetry in the problem where if you don't take the square, everything's going to cancel out and you get something boring. So this RMS distance, we're calculating it to break the symmetry so that we can measure distances. All right. So let's figure out how to do this. All right, and we are going to walk through this in excruciating detail. All right, so let's start out with just one coin flip. So let's start with just one coin flip. So for one coin flip, that is n equals 1. All right, then what we want to calculate is the average of S1 squared. Okay, how do we do that? Well, we learned last week how to calculate any average you could possibly desire. All right, so what we showed last week is that if you have some function and you want to calculate the average of that function, then what you do is you take your function, you multiply it by the probability distribution, and then you sum over all possible values. So that's exactly what we're going to do. So what we're going to do is we're going to take S1 times the probability of any given step. Okay, so whatever the probability of a step is, and then we sum over all possible kinds of steps we can take. Make sense? All right, very good. Oh, excuse me, we have to square things, of course. All right, so let's come down here and let's do this. All right, so L can take on two values, +1 and -1. All right, and again, so S1 is just equal to L1, right? Just because of the way that we defined it. We defined it right here to just be the sum of all the steps that we took. So S1 is just L1. Okay? So when we calculate this sum, S1 squared times P of L, okay, then we have to sum over L equals plus or minus 1. Okay, so in other words, what this is sum of L P of L for L equals plus minus 1, right? Okay, so let's just do it. You just stick it in numbers. All right, so if L equals +1, then L is +1. Excuse me, we have to square it, of course. So +1 squared times the probability of getting +1. Well, that's a half. Okay, plus, what happens if L is -1? Well, so we write in L is -1. And then we square it times the probability of getting -1. Well, that's again a half. Okay, so there it is. So now you can see if these squares were not here, this would just add up to 0, right? That is where, so if you were to explicitly calculate it, that is where this comes from. Okay, so that, the fact that you get a term that's positive and an identical term that's negative and you add them together, that is why the average comes out to be 0. Okay, but now what we're doing by squaring this is that -1 gets mapped into +1. And we've broken that symmetry, and now this thing no longer comes out to be 0. It comes out to be equal to 1. Neat. Okay, so in other words, S1 equals 1. Wow, amazing. So what are we going to do next? 2 coin flips. So now let's look at 2 coin flips. So for 2 flips, okay, so in other words, n equals 2. All right, so now what we want to calculate is S sub 2 squared average. Okay, and so now, again, what this is we're going to take S sub 2 squared times the probability of getting a given set of, whoops, what the heck? What? Times the probability of getting whatever those 2 steps are that give you that value of S sub n, right? Okay, so again, let's do it. So now S sub 2 can take on 4 different values, right? So there's 4 different ways you can get S sub 2. You can take 2 positive steps. You can take 1 positive step and 1 negative one. You can take 1 negative one and 1 positive one, or you can take 2 negative ones. So those are the 4 possibilities of S sub 2. So now what we have to do is take these 4 possibilities and substitute them into this sum and just sum. All right, so let's do it. S sub 2 squared. All right, so first of all, so the first term, let's say, is 1 plus 1. So 2 positive steps squared. All right, times the probability of taking 2 positive steps. So now each step is independent. So the first step has a probability P1, the second one has probability P1, and because they're independent, we just multiply those 2 together. Piece cake. All right, next one. So that's a positive step and a negative step. P of 1, P of minus 1. Plus a negative step plus a positive step. P of negative 1, P of 1. And then 2 negative steps. Oh, and of course, we have to square all these. Like so. All right, so clearly, these 2 terms, because inside these parentheses, I got 1 minus 1 and minus 1 plus 1. This is the kind of math I, as an experimentalist, can do. That's 0. Again, my favorite number. Now you see why it's my favorite number, because it makes these things go away. All right, so we only wind up with 2 non-zero terms. Okay, so this one is 2 squared, so that's 4 times 1/2 times 1/2. Plus minus 1 is minus 2 squared, gives you 4 times 1/2 times 1/2. Okay, oh look, so this is 1 and this is 1. So in other words, the average of S sub 2 squared is 2. So we have S sub 2, average of S sub 2 squared is 2. Average of S sub 1 squared is 1. All right, so now I'm going to go out on a limb here, and I'm going to hypothesize that the average of S sub n squared is n. Okay, so now the way that we are going to prove this is through the power of induction. All right, so the way induction works is that you assume that your answer is true for n minus 1, and then you show that that leads to the answer that you thought it should for n. All right, so in other words, so now let's proof by induction. Stupid thing, induction. All right, so proof by induction is we assume that this is true. And then we show when we take this assumption and we plug it into what we believe S sub n squared should be, that we get what you would expect. All right. So now, to do this, we need to recognize that, so S sub n that means that we have taken n steps. So we would have, so for example, let's do this explicitly. So let's look at, say, S sub 4. Okay, so what S sub 4 is that I take 4 steps. L1 plus L2, whoops, L2 plus L3 plus L4, where again, the L's are random. Okay, but hey, look at this. What is this? Let's say I just group these two together. That is S sub 3, right? So in other words, S sub 4 is equal to whatever I got for S sub 3 plus another step. Okay, and you can always do this. No matter how many steps you take, you can always say that S sub n is equal to the previous n minus 1 steps plus another step. Okay? And now I'm just gonna, what am I gonna do? I'm going to take the square of this, and then I'm gonna average it, like so. All right, so now let's do it. All right, so this is the average of S sub n minus 1 plus L sub n times S sub n minus 1 plus L sub n. And you all remember how to do FOIL from your high school algebra days. So you just write this out, and you get S sub n minus 1 squared plus 2 S sub n minus 1 L sub n plus L sub n squared. Okay, now remember that when we do this averaging, that averaging is just a sum, right? And sums, you can always split sums up in whatever way that you want. So in other words, essentially I can think of these brackets as operators that I can distribute through this sum. And I can write this like, so in other words, I just think of, you know, distributing this bracket through. And what I get is this. Okay. All right. So now, we already have our assumption about what we believe this is going to be. We assume this is going to be equal to n minus 1, right? This. Okay, so now L sub n, that is just the last step that we take, all right? So L sub n can either equal plus 1 or minus 1, right? So L sub n is either plus 1 or minus 1, and then we square it. So that's either plus 1 or plus 1. So the average of plus 1 or plus 1 is 1. So this is going to come out to be just equal to 1. And so now the question is, so in other words, we assume this is true. This is equal to 1. So the only hard part is we got to figure out what that is. All right, so let's figure out what that is. Come on, there we go. All right, so how do we do that? So we want to calculate S sub n minus 1 times L sub n. All right, so now we just do it, right? So we take this function, we multiply by the probability distribution, and then we sum over all possible values. All right, and so if we write it out, what we're going to get is that the probability of 1 times S sub n minus 1 times if L sub n is 1. So in other words, this term is what you get when L sub n is plus 1, plus the term that you get when L sub n is minus 1. And so that's P of minus 1 times S sub n minus 1 times minus 1. Okay, so now regardless of what S sub n minus 1 is, you can see that these two terms are going to be exactly identical. The only difference is this one has this extra minus sign on it. So in other words, my favorite number, 0. Okay. All right. So everybody cool with that? Excellent. So in other words, what we just showed is that S sub n squared is equal to the average of S sub n minus, stupid, S sub n, come on, sub n minus 1 squared minus 1, right? Because that middle term goes to 0. Our last term up here is 1. And we are going to now assume that this is equal to n minus 1. Wait, did I do something wrong here? Oh, right, that's a plus sign. So what we get is n minus 1 plus 1, which equals n. It's exactly what we thought it was going to be. Quod erat demonstrandum. QED. So in other words, we have shown through induction that the average of S sub n squared is just equal to n. Okay, so in other words, the root mean squared value of this, the RMS value, that is, if we take S sub n squared and we take the square root, is equal to square root of n. All right, so now this, let me use a different color. That's a lot of red boxes. That means that's important, okay? So now again, remember that this value, this quantity here is related to the distance that our walker has traveled in this playground. And we have shown that the root mean squared distance that this thing travels is equal to the square root of the number of steps that you take. And so now if anybody comes up to you, like you're walking down the street, one of these days when we can go back outside and somebody's walking down the street and they walk up to you and they say, tell me how far a random walker walks. You should immediately just go square root of the number of steps, okay? So this is something you as a physicist should remember. Okay, now, so that tells us how far on average a random walker travels, okay? So in other words, what we're going to get is some probability distribution. What the? My iPad is too clever for its own good. Okay, so in other words, if I have a collection of random walkers and I let them go, then what's going to wind up happening is that I'm going to get some distribution of where they wind up. It's going to look like this. It's going to be a normal distribution, I believe. Yeah, makes sense. Okay, and so some random walkers are going to go not that far. So on average, they're not going to go anywhere. So you can see the mean here is at 0. Okay, but there is some width to this distribution. So here, this is how far they've traveled, and the y-axis here is frequency. That is how many of them go that far. So what this value here tells you is a measurement of the width of this distribution. Okay, specifically, the width of this distribution is quantified through something called the standard deviation. Okay, so specifically the standard deviation is related to the, this distance from the mean to the inflection point of the curve, technically, is what it is. Okay, and the way that you can calculate the standard deviation is like this. Okay, so given any probability distribution and you start calculating these averages of this distribution, the way that you would calculate it is like this. So it's the mean squared of the distance minus the square of the mean. Okay, so, and then what we have to do is take the square root of this. So that is how you calculate the standard deviation. Okay, so now note this is the mean. How far on average do they go? That is 0. All right. So in other words, the standard deviation of the distribution of displacements for a random walker is equal to that, well, holy crap, that looks familiar. That's what we just calculated, right? So the root mean squared displacement is the standard deviation. That is the width of this distribution. Okay, so this is square root of n. So this distance here, the width of the distribution depends on how many steps you take. The more steps you take, the wider it gets. All right, so now, everybody with me? Okay, very good. So now all this, so technically this discussion has been about coin flipping, right? But I've already sort of given you an idea as to how to think about this in terms of a random walk. I mean, technically, what this distance we're traveling here is just the number of heads minus the number of tails. But now if you throw this within the context of somebody who's walking, what we would say is that what they're doing is randomly taking steps, and they're either randomly taking steps to the right or randomly taking steps to the left. Okay, so in other words, what we've done is write down a mathematical description of a one-dimensional random walker. Okay, so all they're doing is just standing and walking. They're doing this. And what we say is after some amount of time, how far have they traveled? Okay. Okay, and so now what we're going to do is make this connection between random walks. A random walk is going to be our model of Brownian motion. So that's going to be our model of how Brownian motion behaves. Okay, so the idea is that we have our solute molecule, okay, and it's traveling in some direction, and then it collides with a solvent molecule. And that collision makes it change direction, and the direction it winds up going after the collision is completely random. So so you get a collision and then it changes direction. And then you get another collision and it changes direction. And you get another collision and it changes direction, so on and so forth. Okay? Now we're going to say that on average, the time between collisions is what we're going to call delta t. So delta t is the average time between collisions. Thing. Too clever for its own good. So delta t is the average time between collisions. Okay. N is going to be the number of collisions that we have. Okay. And so, in other words, what happens is our particle sits there, or it travels. Okay. So it's traveling after some amount of time, delta t, it undergoes a collision and it goes a different direction. After another time, delta t, it undergoes a collision and goes a different direction. And so each one of these collisions corresponds to our random steps for our random walker that we modeled previously, okay? So the collisions here are what randomizes the steps. Okay, all right, and we're gonna say, again, on average, every step, so this length here that the thing travels, we're going to say on average, they're all the same. All right, so we're going to call that L. So L is the average step size. Okay, and so what we're going to do is we're going to keep delta T and L constant. And the only thing we're going to randomize is direction. Okay, so the collisions randomize direction. Okay, so now this is a simplification, right? But now it turns out that if you go through and you do this, the high-powered, full-on, hardcore, total, you let everything be random, you still get the same damn answer, all right? So we're not, without loss of generality, that's professor talk, without loss of generality, we're going to keep delta t and L constant, and we're just going to randomize direction. All right, so this is what it's going to look like. So we start at x equals 0, y equals 0. Okay, so here's our particle. Okay, and so now what's going to happen is it's going to take a step. So L1 is going to be in some random direction. So it goes this way. So here's L1. Okay, then we have a collision. Okay, so the next step is going to be in some random direction. That's L2. All right, and then we have a collision. It's going to go in another random direction. That's L3. So on and so forth. Okay? So now, the only difference between this and what we talked about previously is now this is in 2 dimensions, whereas what we did previously was in 1 dimension. So now what we got to worry about is the fact that each one of these steps is a vector. Okay? So all these little steps I got to put vector signs on. And what we are interested in is this distance, the total displacement here. That is the distance between the starting point and where we wind up. All right, so this is our total displacement. So what is our total displacement? Well, I mean, you look at this. This is like, you know, the physics 1. This is what you go in and you show the little kitties. Kitties, how do you add vectors? Well, you place them head to tail, and then you draw the vector that starts at the tail of the first and goes to the, that's what this is. It's vector addition. So in other words, the total displacement is just the vector sum of all of these individual displacements. Whoa, that looks familiar too. We just did this. Okay, the only difference is what we did was not vectors, it was only in 1 dimension. But it's still going to be exactly the same idea. All right, so in other words, what I'm going to do is I'm again going to define this variable s sub n, which is just the vector sum of the square of, wait, oh, I'm getting ahead of myself. Don't get too fancy, Professor. All right, so s sub n, in other words, is a vector. And it is just the vector sum of the individual vectors. Okay. So now what we're interested in is the average of s sub n squared, right? Well, so, I mean, again, all is just vectors, right? So this is the square modulus of a vector. So this is just s sub n vector dotted into s sub n vector, like so, right? Or in terms of our previous language, we would say that this is s sub n minus 1 plus the last step dotted into s sub n minus 1 vector plus the last step, right? Okay, so now I just distribute through my dot products. And I get s sub n squared, no, excuse me, s sub n minus 1 squared plus 2 s sub n minus 1 dot L sub n vector plus L sub n squared. Again, I distribute through my brackets. Like so. Okay, so we're almost done here. Okay, so now again, we are going to assume what we did previously. This gives us n minus 1. Because again, it's just a number at this point because it's dot product is just a number. Similarly, this is just a number. That gives us 1. So the only question is, what is this? All right, so in other words, we need to calculate s sub n minus 1 vector dot L sub n vector. All right, so again, we go back to our basic introductory physics. You can write this as the magnitude of S sub n minus 1 times the magnitude of L sub n times the cosine of the angle between them. This is just a constant. That's just our step size. Might be plus, might be minus, doesn't matter. This is the sum of all of our, this is the displacement of all of our previous steps. So the only variable here is the angle at which this last step is at. So in other words, what I'm saying is that this is equal to this. So in other words, we just need to calculate the average of cosine theta. What is the average of cosine theta? Well, you can just look at the damn thing. There's cosine theta. What's the average of that? 0. Okay, so in other words, in 2 dimensions, turns out this is still true. The average of S sub n squared is still equal to n. So in other words, the root mean squared displacement is just equal to the root mean square, the number of steps, times the average step size. So in other words, what we get is that the average displacement of a random walker in 2D is square root of n times the step size. Big red boxes. All right, so that is our description of the average behavior of random walkers. Ta-da! And so we're done for today. And so now what we're going to do is on Wednesday, I'm going to show you how now you take this statistical understanding of how random walkers behave, and we will derive diffusion. I will show you that diffusion happens. Okay, so any questions? No. All right, then I'll see you guys on Wednesday.
Thank you.
Yep, toodaloo. Oh, I shouldn't have said toodaloo. There we go, toodaloo.